substances that form our world are composed of atoms held together by powerful electrical forces we call chemical bonds. Why do some substances drop and bounce, and some substances drop and break, and some substances just drop and stay there? Why do some substances remain solid as they're heated, while others liquefy quickly? And when substances interact, why is energy always required or given off? The physical and chemical properties of elements and compounds, to a large extent, depend on the nature of the bonds and weaker forces that hold their atoms and molecules together. Keep in mind, as we visualize atomic structure, that there is no way to show relative sizes correctly. The diameter of the average atom is 10,000 times as large as the diameter of its nucleus. If an atom were enlarged so that the goalposts of a soccer field passed through its outer limits, the nucleus would be no bigger than a pea, right in the middle of the field, about a centimeter in diameter. The interaction of the charged particles that make up atoms is the key to bonding. The attractive force between the positive charges of the protons in the nucleus and the negative charges of the electrons at various energy levels around the nucleus hold the electrons in the atom. When two atoms approach each other, there is an attractive force between the protons in the nucleus of one atom and the electrons in the other. All chemical bonds are formed in this way and create matter in its various forms. Elements, when atoms that are alike are bonded together, and compounds, when atoms that are different are held together by chemical bonds. Chemists have devised models for the different kinds of bonds, descriptions that help them and us to account for the properties of elements and compounds and to predict their behavior. The most significant kinds of bonds to chemists are those that form and break during chemical reactions. But it might be easier to understand their nature by first dealing with a type of bond that explains only the physical properties of one group of important substances. Our technological world, our high-tech world of complex structures and amazing devices, could not have developed without metals. In communications, construction, transportation, in the great electronic revolution, metals are essential substances and used in vast quantities. In all living organisms, compounds of metals are no less essential. Metal compounds are basic to many life processes. In the periodic table of the elements, metals are all found in the same general area, and most of them have a number of similar properties that can be explained by the metallic bond that is found only between atoms of metals. This type of bond, like all bonds, is based on electronic structure. We can consider the structure of the metal sodium, for instance, as a typical case. A sodium atom is electrically neutral. In its outermost energy level, it has one electron. This is called a valence electron. Valence electrons are involved in bonding. This single, highly energetic outer electron is so weakly held by the nucleus of its atom that, in a great aggregation of such atoms, the effect is this. There is a sea of negatively charged valence electrons flowing among regularly arranged atoms that have lost their permanent outer electrons. This gives the atoms a positive charge, so we can call them ions. It's the attraction between the positively charged ions and the negative sea of electrons flowing between them that bonds all the atoms together to form the metallic elements. Under the microscope, we can watch metallic bonds forming as atoms of the metal silver arrange themselves into the very precise structure known as a crystal. A repeating pattern called a lattice is under construction. As the atoms move into the lattice, they free their electrons and become positive ions. The metallic bond can explain the similar properties of metals. Why do metals tend to have a shininess? Light waves are involved. Light waves have a certain frequency of vibration. They cause the sea of electrons on the outer surface of the metal to oscillate at the same frequency when the waves strike them. When this added energy is radiated away by the electrons, we see it as a reflection of light. The surface looks shiny. These mobile outer electrons, attracted to positive ions in all metals, also can account for many other properties that are characteristic of metals. When there's a voltage difference across two parts of a metal, the electrical force easily produces a movement of the free electrons. This accounts for the high electrical conductivity of metals. Metals are also good conductors of heat. Heat produces a high kinetic energy in the free electrons that are part of the metallic bond. Because they're highly mobile, they move and give up their extra energy to electrons with less energy. And these electrons pass their new energy on in the same way. For this reason, heat is easily conducted through a metal. Metals are malleable and ductile. Under physical pressure, the lattices that form the crystals of metals will reshape themselves. Rows of ions in the lattice separate, slipping past one another. But as long as the separation is not too great, the attraction between the sea of electrons and the ions, that metallic bond, is strong enough to keep the metal from breaking apart. Instead, the lattice simply takes on a new alignment. The metal changes its shape without breaking. The metallic bond is pretty much the force that holds together our metal-based technological society. In metallic elements, all the ions attract all the electrons, and the ions are all of one kind. In a second kind of bond, the attractive force is produced between ions alone, ions of different substances. When an active metal, like sodium, interacts with an active non-metal, like chlorine, the result is one of our most familiar compounds, ordinary table salt, sodium chloride. Like metals, salt forms crystals, and an X-ray of a salt crystal shows a structure similar to the one we see in metals, a lattice of regularly arranged parts. But there are not many similarities in properties. Salt crystals are clear and tend to bend light rather than reflect it as metals do. Salt crystals are very brittle. They shatter easily, not like metals. Does salt conduct electricity? No, not as a solid, only when molten. And the boiling points and melting points of salts in general are relatively high. The melting point of table salt, for instance, is 800 degrees Celsius. This is more than 700 degrees higher than the melting point of the metal sodium, one of its constituents. The bond that holds these substances together is named for the kind of particle that forms them. It's the ionic bond, formed by the force of attraction between positive and negative ions. The particles in a salt crystal are ions, as they are in metals, but the ions in a metallic element are all of one kind, and all positively charged. In salt and other ionic solids, this is not the case. We can see why if we consider what happens when just one sodium atom interacts with just one chlorine atom. A look at the periodic table tells us something about these atoms. Sodium is the first element in its period. Aside from the single valence electron in its outermost energy level, sodium has the electronic structure of neon, the noble gas, a highly unreactive element. Chlorine, on the other hand, is the next to last element in its period. It has 7 electrons in its outer level, just 1 electron short of the 8 that argon has, which is just as unreactive as neon. Now, as we bring the sodium and chlorine together, with enough energy and close enough to interact, powerful electrostatic forces come into play. The forces move the single electron from the outer level of the sodium atom to the outer level of the chlorine atom. But with 1 less electron, the originally neutral sodium atom now has an excess of 1 positive charge. And the originally neutral chlorine atom, in gaining 1 electron, now has an excess of 1 negative charge. And so, both are ions, charged atoms. The 2 ions are held together in this ionic bond. This same force of attraction draws ion after ion into an arrangement that is very precisely determined by the electrostatic forces and the sizes of the ions involved. The ions pack themselves into a lattice, which gradually grows into an ionic crystal of table salt. The ionic bond can help explain the properties that we usually associate with table salt and other similar ionic compounds. Why are salt crystals transparent, not shiny like metals, which are also formed of ions? In the metallic bond, the free-flowing sea of outer electrons absorbs and then gives off the energy from light waves. But in ionic crystals, the outer electrons of both ions are bound tightly in the same configuration that the outer electrons of noble gases have. So the energy of light is not absorbed and re-radiated. Instead, light waves tend to pass through the crystals and make them appear transparent. Why is a salt crystal so brittle? When the crystal is stressed, the orientation of its positive and negative parts is changed. Positive ions were around every negative ion, and negative ions around every positive ion. But now, ions with the same charges come in close proximity to each other. And what happens? Repulsion, because like charges repel. And so the structure breaks apart. The crystal shatters. And as for electrical conductivity, even though all the parts of the salt crystal are charged, positive and negative ions, no charged parts are free-flowing, like the sea of electrons in a metal. They're all locked in place. So when a voltage difference is applied to the solid salt, there is no movement of charged particles. For the same reason, heat energy is not transmitted well through salt and other ionic substances in their solid phase. And boiling and melting points are high because ionic bonds, particularly between active metals and nonmetals, are very strong. When salt melts, the bonds that hold the ions together break, and the ions are no longer held in their rigid structure. Now a voltage difference has an effect. Free to move, negative ions in the molten salt are repelled by the charge on the negative electrode. Their movement toward the positive electrode constitutes a flow of electric current. But because ions are considerably heavier than electrons, they're more difficult to move. And so a molten ionic substance does not conduct electricity as well as a metal does. So we've dealt with atoms of metals that form elements with metallic bonds, and atoms of active metals and nonmetals that form compounds with ionic bonds. Now, to illustrate a third kind of bond, let's look at sulfur. Sulfur, like very few elements, is found in nature in its nearly pure form and is a non-metal. It's not much of a conductor of electricity, either in its liquid phase, as salts and metals are, or in its solid phase, as only metals are. Now, take a compound, water for instance. It doesn't conduct electricity very well either, neither as a solid nor as a liquid. Water is formed from two nonmetals, hydrogen and oxygen. These elements will also not conduct electricity easily in any phase. So we can reasonably conclude that neither free electrons nor ions are part of these substances. What sulfur, water, hydrogen, and oxygen have in common is that each is made up of molecules, two or more chemically bonded atoms. 8 atoms of sulfur bond together to form a single molecule of sulfur. 2 atoms of hydrogen and 1 atom of oxygen bond together to form a single molecule of water. 2 atoms of hydrogen form a molecule of that gas. 2 atoms of oxygen form a molecule of that gas. A molecule is the smallest unit of a substance that retains the chemical properties of that substance. Let's first consider the atoms that form the hydrogen molecule. A hydrogen atom has 1 electron in its outer energy level, 1 valence electron. To explain how 2 such atoms bond, we have to assume that when they approach close enough to each other, their outer levels overlap, and their outer electrons are shared between the 2 atoms. Both outer electrons are attracted by the positive charges in both nuclei at the same time. Because the bond is formed by the 2 atoms sharing a pair of valence electrons, it's called a covalent bond. Co is a prefix that means with or together. Covalent bonds are usually found between atoms of non-metallic elements and are very strong. Most normally gaseous elements, like hydrogen and oxygen and iodine, are in the molecular form. These are crystals of iodine forming, made up of regularly arranged molecules, each molecule containing 2 atoms of iodine. The covalent bonds that hold the atoms together in the molecules are strong, but the forces that hold the molecules together in the crystal are weak and don't involve a sharing of electrons. Because these forces, which are called van der Waals forces, are so weak, it doesn't take much energy to break the molecules out of their crystalline arrangement. So iodine has a very low melting point and boiling point. In fact, at room temperature, iodine sublimes. It goes directly from the solid into the gaseous phase. For the same reason, ice, which is water in its solid phase as a molecular crystal, is rather fragile. But water molecules themselves are very stable. In the water molecule, an oxygen atom with its 6 outer electrons shares the single outer electron of each of 2 hydrogen atoms. In effect, through these shared pairs of electrons, each atom now has the very stable configuration of a noble gas. Hydrogen has 2 electrons in its first energy level, like helium, and the oxygen atom now has 8 in its second, like neon. The number of valence electrons determines how many additional electrons can be shared. Because oxygen has 6 outer electrons, it has room for 2 more to give it a noble gas configuration of 8. Except for hydrogen, with its capacity for only 2 electrons, the vast majority of covalent bonds result in 8 outer electrons. Because it happens so regularly, this way in which electrons are added is called the octet rule. And so nitrogen, which has only 5 outer electrons, following the octet rule, tends to add 3 electrons to its outer energy level. It can do this by bonding covalently with 3 hydrogen atoms. 3 pairs of electrons are shared between them. Each hydrogen atom supplies 1 electron to the nitrogen atom, and each hydrogen atom shares one of the nitrogen's electrons. And all have noble gas configurations. Carbon atoms can form a maximum of 4 covalent bonds. So a carbon atom can bond covalently with 4 atoms of hydrogen. 4 pairs of electrons are shared, forming the familiar fuel, methane, natural gas. Carbon atoms can also bond with other carbon atoms to form chain-like molecules, making possible an immense number of variations. There are more compounds of carbon than of any other element. Carbon compounds are the basis of all life. The tremendous variation offered by carbon has made possible such complex molecules as DNA, which is composed of thousands of atoms. The complexity of DNA is the result of the same covalent bonds that hold together the simple molecule of water, the result of attraction between charges in the molecule. Now, charges in covalent molecules may do more than just hold the atoms together. In the water molecule, for instance, these charges are not equally distributed. The oxygen side tends to be more negative, and the hydrogen side more positive. A polarity has been produced. In general, covalent bonds between atoms of different elements are usually polar and result in what we call a polar bond. But covalent bonds between like atoms are nonpolar. The molecules as a whole are balanced electrostatically. Polarity usually forms when different kinds of nonmetallic atoms bond covalently. Which kind of bond is likely to form between atoms is related to certain periodic properties of the elements. One of the most important of these is electronegativity, the measure of an atom's tendency to attract electrons. Generally, electronegativity increases as we move across and up the table toward the more nonmetallic elements. The greater the difference in electronegativity, the more likely it would be that two atoms would form an ionic bond. The smaller the difference in electronegativity, the more likely it would be that electrons would be shared between atoms in a covalent bond. But the fact that electronegativity gradually changes across the table points up the fact that there can be no sharp boundaries between the different types of bonds. In nature, the divisions between bonds are blurred. Chemists have worked out these fine distinctions only to help themselves and us understand the structure and properties of the incredible number of substances that make up our world.